The objective of the group project was to design, build and test a wing spar that had minimal mass while meeting design requirements. This process included 4 design steps.
We began by considering beam shapes, and we realized that the circular beam was shown to be strong in resisting torsion but quick to deflect under a point load.
The triangular beam would be good at resisting torsion, however it cannot withstand large point loads such as the ultimate load. During the first lab, we sketched and created prototypes of an I and rectangular beam, getting a feel of the foam board's properties. The I beam carried a larger load, but its torsion was higher, causing deformation. We settled on a rectangular beam as it had a lower tip deflection and torsion due to a larger second moment of area. Determined through using the theory, checking our Excel values, and working out the largest stress would be at the base. To create a larger second moment of area, the equation suggested our base be smaller than the height. However, the polar moment was key to ensure the spar fit torsional compliance, so we made both dimensions large to reduce tip deflection, but made the base larger than the height. The polar moment of area is determined by spar thickness. To make the moment large, we used 2 layers of foam board on each side.
We adjusted the coordinates of our chosen beam dimensions to fit into the desired aerofoil. We started with rectangular beams and noticed the greatest moment effect at the support, hence we opted to initially increase the thickness, then decrease it at the loaded end as torsion effect was still passed. So
we created a staircase design increasing in thirds, the densest end being clamped to reduce the moment. This decreased tip deflection, which is inversely proportional to max stress, allowing the spar to carry the ultimate load. During testing, our folded spar could withstand twice the load of the glued one while also being lighter. Also, the hot glue made our spar heavier and thicker. We settled on folding the external and internal net of the spar and gluing and hand cutting the smallest steps. We tested this by hanging weights using a rubber band at the spar's tip, but realized clamping the spar directly would damage the base, which is key to manage the stress load. So we 3D printed a clamp attachment that had tolerance on either side and a weight holder to evenly distribute the load at the spar's tip. We also printed a torsion attachment the weights could hang from. CAD simulations were used throughout to check tip deflection and torsion met the design requirements.
after modeling, testing, and finalizing our spar design, we integrated our spar with other wing structures, including aerofoil ribs, aileron, and flaps.
After building and modeling our final spar design, we tested it under a load factor of 1 and got a tip displacement of 7 mm, passing the requirement. The spar also passed the 2.5 ultimate load factor requirement and did not break under ultimate load. This could largely be due to the transition between glued to folded spar. Due to the time constraints and 3D printing schedules, we were unable to print the parts for our torsion testing on time. To test the torsion before the final demonstration, we could have also used the topology optimization feature on SolidWorks to be able to reduce the mass of the spar by cutting the unnecessary parts without sacrificing the integrity of the structure.